Today we are jumping into a really foundational paper, Detailed Balance in Large Language Model-Driven Agents by Ziyang Song and colleagues. The big idea here is, well, it's pretty ambitious, trying to establish a physics-like theory for how these complex AI agents actually behave.
It's a huge shift in perspective. For the longest time, we've treated these incredible agents, things like FunSearch or AlphaVolve, as these super intricate engineering projects, basically a black box that we poke and prod by changing prompts. This paper says, no, there might be a macroscopic physical law underneath it all.
And for anyone just tuning in, what's that 1-minute summary? The key insight.
The core finding is that LLM state transitions show something called detailed balance. Now, that's a property you normally find in physical systems at equilibrium. Think gas molecules in a box. What it means here is that the LLM isn't just learning a set of rules, it's implicitly learning an underlying potential function. They call it $.
A potential function, so like an energy landscape for ideas.
Exactly that. This $. Gives a quality score to every possible state, creating this global map that gives the agent direction. And it doesn't matter what prompt template or model you're using. And that's massive because it moves the study of AI agents from, bit of a craft, more towards a predictable, quantifiable science.
Okay, but hold on. That immediately throws up a question for me. We all know these agents are built to do things, to find solutions. They're iterative, they're goal-seeking. How can a system that's actively trying to get somewhere new be modeled as an equilibrium system? That feels like a direct contradiction.
That's a fantastic question. It's actually the exact tension that the paper digs into. The key is the scale you're looking at. So yes, the agent as a whole is driving toward a goal that's non-equilibrium. But if you zoom in and look at the vast landscape of all possible states it could be in, the probability of moving between any two of those states often follows that equilibrium rule. It's sort of like a river. The whole river is flowing downhill, but the little eddies and swirls between two rocks can be described by local balanced conditions.
Right. Okay, that analogy helps. So let's unpack that framework. We've got these incredibly powerful agents doing things like scientific discovery, but we really don't know how they're thinking. We can count tokens, sure, but that's a microscopic view. We need this macroscopic picture.
And to get that picture, they model the agent's generative process as a Markov transition process, which is just a formal way of saying the agent moves from state to state, and its next move only depends on where it is right now.
Okay, let's be super clear about what a state is here, because it's not just a word or a sentence.
No, absolutely not. A state, which they might label 5 or 10 or dollars, is the entire information packet the agent has at a given moment. It's the task objective, the history of what it's tried, the code it's written, API calls, everything, the full context.
And the chance of it moving from one of those big complex states to another one, DIA, is the transition kernel. But since these agents have a goal, that transition isn't just random. There's a preference.
A definite preference, and it shows a clear structure. That's what leads them to hypothesize this underlying potential function, $. You mentioned the energy landscape, and that's the perfect analogy. Think of it as a topographical map. Every state has an elevation, and the agent, well, he just wants to go downhill to find better states.
I love that analogy. It makes it so much more intuitive. But how on earth do you measure this invisible map? This is where they bring in the big guns from physics, right? The least action principle.
That's it, exactly. In physics, an object follows the path that minimizes action. So they applied that same idea. They defined the action. $7 is basically the total mismatch between what the agent actually does and any potential function dollars you might guess.
So if you just make up a random potential function, your action dollar is going to be really high because it doesn't match reality.
Precisely. The goal is to find the one true potential function, $, that makes that action $7 as small as possible. It's this minimization principle that lets them extract the LLM's own internal sense of direction.
And that leads straight to the smoking gun for their whole theory, the detailed balance condition.
It really is. In equilibrium systems, detailed balance says the flow of probability from state phi to state dollar has to equal the flow from $d back to dollars once you account for how common each state is.
Let's break that down for a second, because if the agent is always getting better, you'd think the probability of going from a bad state to a good one would be way higher than going backward.
You would, but that's where the scaling factor comes in. If the good state, $d is really rare, and the bad state, $2 is super common, then the high probability of moving forward is balanced out by the rarity of the destination. So even with this clear forward progress, the underlying math of the system can still be symmetrical.
And that symmetry is what lets you connect it all back to the potential function, raw dollars.
Yes. If detailed balance holds, you get this beautiful direct relationship. The logarithm of the ratio of the forward and reverse probabilities is just the difference in their potential. It literally means the agent prefers to move downhill. Finding that this holds for LLMs is what suggests there's this universal law at play.
Okay, so a very elegant theory. Now for the hard part, proving it. They started with a simple constrained task, didn't they? Conditioned word generation.
They did. The task was generate a word where the sum of its letter indices is exactly 100. They ran it 20,000 times for a few different models to estimate all those transition probabilities.
And this first test immediately split the models into two camps.
Oh, dramatically. You had what they call the convergent models, which were Claude 4 and Gemini 2.5 Flash. They basically found one or two good answers and then just got stuck. They showed almost no exploration. Claude found only 5 valid words. Gemini only found 13.
Only 5. Wow, that sounds brittle, like it's getting trapped in the most obvious answer.
They called it the low-temperature trapping phenomenon. It's a direct physics parallel. The system gets stuck in a valley because it doesn't have enough energy to explore other, maybe better, valleys. They even saw Claude start generating invalid words after a while. It was so stuck, its reasoning actually started to break down.
A classic exploitation over exploration problem. So who was the explorer?
That was GPT-5 Nano. It was completely different. It generated 645 unique, valid words. Its behavior was so much richer, and that gave them the data they needed to actually test for detailed balance.
And they did that using closed paths, right? Like going from state A to B to C and then back to A.
Exactly. If this potential function idea is right, then any round trip you take on that map has to bring you back to your starting elevation. The net change must be 0.
And for GPT-5 Nano, they checked 140 of these different loops, and the results all clustered right around 0. It was a beautiful verification.
So the theory holds up for a toy problem. But the real test is a complex, real-world agent. They scaled up to the idea search fitter agent, or TRIAL, which does symbolic fitting. This is a much harder problem with long reasoning chains.
And this was the crucial step. The scale here was just enormous. They had a database of over 50,000 state transitions between nearly 7,500 unique states. And remember, a state here is a whole complex mathematical expression.
Did the law still hold?
It did. Detailed balance was statistically verified again, which is powerful evidence that this isn't just a fluke of one task, it's something fundamental.
And they went even further. They actually found the explicit formula for the agent's potential function, VDLO-tolers. What did that formula tell them about how the agent thinks?
This is where it gets really practical. The function, $, didn't care about surface level stuff, like the length of the string. It cared about deep structural features of the mathematical expression. It had penalties for complexity, length, and most importantly, risk. For example, it would heavily penalize an expression that had a risk of dividing by 0. It had this built-in sense of mathematical safety.
So $, is like a mathematical model of the LLM's own intuition about what makes a good or safe idea, completely separate from whether that idea actually works on the data.
That's a perfect way to put it, and they proved it. When they looked at the most likely transitions the agent made, a whopping 69.56% of them were moves that decrease this internal potential function. The agent is almost always trying to move downhill on its own internal map of what feels right.
Which leads to what might be the biggest takeaway for anyone building these things: the potential clash between the agent's internal goals and our external ones.
Yes, this is the mic drop moment. They found that LLMs will consistently choose states that have a low potential value states that are simple, safe, and clean, even if those states are worse at solving the actual problem. A state with a low potential might not give you the lowest mean square error, for instance.
Hold on, so you're saying the agent is hardwired to prefer an elegant, safe, but maybe wrong answer over a messy, complex, but correct one?
In a sense, yes. Its internal cognition, this $, prioritizes structural integrity and, well, safety over raw performance. This explains so much about why agents sometimes just seem to get stuck on a problem. It's not that they can't find the answer. It's that the answer lies in a part of the map that their internal compass tells them is dangerous or bad.
That is a fundamental insight. So if your agent is stuck, the problem might not be your prompt, but a mismatch between its $, and your objective function.
Precisely. You need to check both. Is the MSE high because it's in a high $, area and still exploring, or is it stuck in a low $, area that's just a dead end?
So the big summary here is that detailed balance is this universal law for LLM agents, at least at the macroscopic scale.
And this framework actually gives us a lever to pull. We can use the action, that value we minimize, to find $, in the first place to control the agent. S is basically a measure of the agent's temperature. A small $1 means it's moving very deliberately downhill. A large $1 means it's jumping all over the map.
Which gives us direct, quantifiable advice. At the start of a search, you want to tune your hyperparameters to lower the action, seal dollars, to make the agent more focused and efficient.
Absolutely. You want that strong directional push, but later on, if you see it getting trapped in one of those low-temperature basins like the Claude model did, you need to turn up the heat. You adjust your parameters to increase CLRs. You force the agent to become a mutation core, to explore more erratically and hopefully jump out of that rut.
The ability to tune that exploration-exploitation trade-off using a real physical parameter from the agent's own dynamics, that's a huge step forward.
It is, and the paper points to the future, suggesting we could even use this to detect overfitting. An overfitted model might have a very fragmented, non-equilibrium landscape, whereas a robust model has this smooth, global potential function.
It really is an incredible achievement. It provides a rigorous scientific framework for something that has often felt more like an art. It's giving us the tools to engineer these agents with real predictability.
It really does. And since we now know this potential function $V can give us the characteristic energy scale of an agent's moves, here's a thought for you to chew on. Imagine you have a complex agent running live, in production. How could you set up a system to continuously sample its transitions, just a few here and there, to monitor its actions, isottle dollars in real time? Could you use that to detect if the agent's internal cognition is starting to drift away from its mission before it starts making bad decisions?
A real-time cognitive drift detector for AIs. It's a fantastic idea and a great place to leave it. For anyone who wants to get their hands dirty with this, the code for the Idea Search Vidder agent and the word generation experiments, plus all the data, is open source on GitHub and Hugging Face.